All right, thank you, everybody. So my name is Luyi Xing. I am an assistant professor from Indiana University, Bloomington. So today I'm going to talk about some security problem in IoT access control. Some novel attacks in the mobile as a gateway IoT. So today I'm going to speak on behalf of my team. So we have more team members, including student researcher Xin'an Zhou, student researcher Jiale Guan, and my collaborator, Professor Zhiyun Qian from UC Riverside. So this is the team for this project, and in the past we have been frequently speaking at the Black Hat and for multiple topics, including IoT. For IoT security, here are some of the past talks by my team since many years ago. So today we are going to talk about a specific kind of IoT. We call it mobile as a gateway IoT. In short, we call it MaaG IoT. In short, MaaG IoT leverage the mobile phone as an internet gateway to communicate with the IoT cloud or server. And MaaG IoT, it lacks persistent internet connectivity. It relies on the mobile phone when it is nearby to talk with the cloud. To better understand this emerging IoT paradigm, let's take a quick review of all the different major IoT architecture in the world. In the early days, IoT doesn't really need a server, and people usually use their mobile phone to control their IoT locally. For example, a lot of sports bands doesn't really need a server. This is the most simple, very simple paradigm of IoT. And later, especially in the recent few years, and the IoT is often based on the cloud. We call it a cloud-based IoT, or actually more specifically, cloud-centered IoT. The cloud in the middle. The cloud sits in the middle. That's a device. That's a mobile phone. That's IoT. The IoT device is connected to the cloud through Wi-Fi, through IoT hub that supports Zigbee, Z-Wave. They have persistent connection to the cloud, and the cloud in the middle. And any control command goes from the mobile phone to the cloud in the middle. The cloud performs all the access control mediation, and only authorized command can go to the device to control the device. So that's a cloud-centered IoT. That studied a lot, including studied by our team. And then here is the paradigm that we are going to talk about today. We call it mobile as a gateway IoT. So this is a emerging paradigm that it still leverage the cloud like the original paradigm. It also leverages the cloud for centralized traffic management. Traffic management means the user management, usually. It leverages the cloud for centralized traffic management and device management, device deployment. It leverages the cloud. In the meantime, to reduce power. In the meantime, these devices lack persistent internet connection. So for reduced power consumption, for reduced manufacturing cost, they do not come with like a Wi-Fi module or internet module. They do not have persistent internet connection. Nor do they require that kind of internet connection to work. So rather, these devices leverage the user's mobile phone to act as an internet gateway. And when the phones are nearby, the phone can help relay information between the device and the cloud, exchange policy, etc. Also, there's a unique feature here. So That's a unique feature here. So these MaaG devices, they feature local access control. So that means not all the IoT communication has to go through the cloud all the time. For example, if a user just local to the device, the command doesn't really have to go through the cloud. So this is different from the original cloud-centered IoT that every command, even if you're at home, you are local to the device, your command have to go through the cloud. In this version, in this new MaaG IoT, if you are local, your command does not have to really go through the cloud. You can just locally communicate with the device, and the device will enforce the access control. Even if the cloud is down, even if there's a network partition, and the user can still access the device locally. So we call this a new paradigm. This IoT paradigm at the mobile at gateway IoT or MaaG IoT. In this MaaG IoT, the device and the cloud split security responsibilities. They both do access control. The local authority, remote authority, they both do access control. They have to split the security responsibility, and thus they have to coordinate their security access control. So to make sure the overall system is secure, that is unauthorized user, unexpected user should not really access the device. So this brings in new security challenges when the two authorities need to really coordinate, and bring in new design level challenges. So overall, we purchased actually 10 real-world IoT devices, mainly smart locks and a few other location trackers from popular mainstream vendors, and we reverse engineered their protocol for access control and confirmed that they are all vulnerable under this MaaG IoT paradigm. So these devices are actually very popular. For example, the autographed lock, Jiale lock, like a Honeywell. I'm not sure how popular they are in Asia, but they are super popular in the United States. Some of their mobile apps have like more than 5 million or more than 1 million downloads on Google Play. So we confirmed their security critical flaws in their access control, and which allow unauthorized user or low privileged user to escalate to gain unexpected control over IoT devices. So altogether, we identified a bunch of security flaws. We put them into 2 categories. We will detail this later. So let's look at our threat model, which we consider, which we think are very practical. So we consider the IoT cloud infrastructure and the system are benign, and the cloud, the network infrastructure, the IoT devices, firmware, software, they're all benign. We consider that even if they're all secure, we still identify new threats, even if those are all secure. And we consider the current device sharing or more generally delegation scenario that device owner and administrator, they often have to share devices to guests, to Airbnb guests, to house guests, to employee, and those permissions are subject to revocation. And as a low privileged user or as a guest user, as an employee, he may be malicious. He may want to escalate the permission. He may want to retain access even after his permission is revoked. Also in this talk, when I refer to app, I always mean the IoT vendor, the mobile app. This is compared to many IoT cloud-side app. Okay. So we identify a few fundamental challenges in the design of MaaG IoT. So first, let's recall the original cloud-centered IoT. So as we mentioned just now, all communication, all command go through the cloud for centralized mediation. So the cloud is the only access control point, is the only authority here. However, in the new MaaG IoT, the access control is much more complicated, in the sense that in MaaG IoT there are two authorities. Both the cloud and the device are responsible for access control, and they both maintain access control policies. They both make access decisions, and they have to make sure their decisions are consistent. So that's a challenge here. That's a complication here. So the cloud side policy and the device side policy have different complexity. The cloud usually, the access model in the cloud usually more complicated, maintain more semantics, more granularity, and on the device side, usually the policy is simpler. It had to be similar. It had to be simpler. We'll talk about this later. Why? So the two different access models, on the device side, on the cloud side, they have two different access control models, access policy models, but they have to coordinate to make sure they are consistent and to make sure they make the same decision all the time. And that makes it very difficult. So note that if you are familiar with the prior decentralized access control into the distributed system, this is different here. So in the prior decentralized access control, usually the system generally assume that all system components use the same global unified access control model. So here, the cloud and device, they have different access control model, which we will detail shortly. So that makes them difficult to coordinate to make the same access decision. So let's look at a little bit more detail in this access control here. So in this MaaG IoT, the cloud generally served as the authority to manage policies. Usually a device owner use the mobile phone to control policy, to manage user, add user, grant user, revoke permission. These policies are recorded on the cloud side policy. And but usually when the user is local to the device, the user accesses the device, it is often the device that enforces the policy. Not all the, as we said, not all the traffic had to go through the cloud. And in the access model, the cloud can support increasingly complicated access control semantic. For example, user role, delegation relation, then the permission, location-based permission. It can be increasingly complicated in the cloud. But in the device, it cannot maintain that much access control semantic. It has to be simpler. And for considering the power consumption, considering the difficulty in updating firmware, it must be simpler. For example, a smart lock does not need to really aware of the user, the delegation relation, who grant permission to this user. The device only needs to make sure it serves the legitimate user. It denies the illegitimate user. It doesn't have to care about user delegation relation, etc. in the cloud. So to support the access control, the real-world IoT manufacturers developed a mechanism to convert the cloud-side complicated policy to the simpler version on-device policy. We call this process the access model translation. So the device does get a policy from the cloud, but get a simpler version on the device to enforce. When the user operates the device, the device uses the simpler version to enforce the policy. So let's look at a little bit more detail in this access model translation. So on the cloud may support in the cloud access control model. It may record the user ID. The cloud supports user authentication, username, password. The cloud records the user roles, the user permission, the user DR delegation relations, and on the device side. In the device side access control model or policy, it doesn't want that much information. Or it cannot even support that much information. For example, the device may not support authentication with the user, so the device may not even store the user ID. To make sure the whole system works, to make sure the device knows who is the right user, who is the authorized user. So usually the cloud uses the private key to sign a credential, and give it to the device for a specific user. So later, when the user presents the same credential signed by the cloud when the user presents the same credential to the device, okay, the device knows that, okay, this user is authorized. This credential is signed by the cloud. So the device side usually just maintain this credential to know, okay, which is the right user. So the key question here is whether the on-device policy really maintains sufficient semantic information, so commensurate with the complicated cloud-side policy. So the AMT process just translates complicated cloud-side policy to the simpler version of the device-side policy without a standard security-assured mechanism for this AMT process. We find that the mainstream IoT vendors generally failed to preserve sufficient information on the device-side policy, and consequently, when the device model does not have sufficient information, it cannot always make the same access decision, same with the cloud, that leads to security critical access control problem. But this process was never seriously, rigorously analyzed before. So let's look at one example. So this figure outlines the AMT process of a real-world lock called a quickset or RORO, quickset of smart lock. The phone in the middle, this is the lock. This is the quickset backend server. We call it quickset cloud. So when the user for the first time the user wants to access the lock, the user goes through a protocol. The user sends a request to the lock. The lock generates a challenge string called is lock. The user presents this string to the cloud. If this is the legitimate user, the cloud will sign on this string. We call the signature CR or credential. The legitimate user then presents this credential to the lock. The lock can then verify the signature, and it assures that, okay, this user is legitimate. The cloud signed this for this user. And then at step 7, the last step, the cloud establishes a Bluetooth binding relation with this phone, following the standard Bluetooth BLE pairing and binding process. And then later, for the following operation on the device, the user does not have to go through the whole process again. The lock already recorded this binding relation with this phone. So after this binding, let's look at what's in the device side policy. So the device side keeps a record of the binding relation with this phone. The phone BLE level, phone name, binding name, and the BLE level binding key to maintain this Bluetooth connection. We also found that after this binding, after this whole process, the lock side dropped the CR, dropped the credential originally signed by the cloud. So this is in the, okay. There are multiple problems in this AMT process of the quickset lock. So the first is the loss of identities in the device side policy. So because the device-side policy does not maintain the user identity or the original user-related CR, so it is problematic when the real owner wants to revoke a user. So actually, based on the user menu provided by the vendor by QuickSet, the owner, if he wants to remove a user, he should use his mobile app to select a user ID he wants to remove, and that actually only removes the user record from the cloud-side policy. Okay, that user ID is removed. And that user is no longer able to go through this whole process, no longer get a new credential assigned by the cloud. However, the in-device policy still remains. The binding relation is still there. That user who should have been removed can still connect with the device and can still operate the device, even though his permission had been revoked from the perspective of the owner, from the perspective of the cloud. So in our study, we find that to be really secure for the owner, he had to, even though this is not made clear by the vendor, but we find that the owner had to go physically near the device and use the app and open a specific GUI of the app. That GUI in the app will query the log and automatically query the log and list out all the binding relation recorded on the log. And the owner can choose from the list and decide, okay, based on the name, which binding relation he wants to remove. Okay, but even with this is still problematic. Even if the owner knows this is still problematic in the design. So this phone name not reliable. This phone name was provided by the malicious user the phone, by the guest user the phone. This name not trusted. And the malicious guest user who should be removed may originally provide a deceptive phone name. So this will make the owner very difficult to really find out the right binding relation to remove it. So in summary, the AMT process of this QuickSet lock lost identity in the AMT process, lost identity in the on-device model, and make it hard to map back the on-device policy to policy on the cloud. Whenever there's a policy update on the cloud, it's difficult to update the corresponding policy record on the device. Yeah, of course, we in our study we implemented end-to-end proof of concept attacks on the real devices, and the vendors. Any attack that I talk about today, acknowledged by the real vendors with the proof of concept attacks. All right. So in general, our study showed that without a principled security guideline and approach, to the real-world manufacturers, when they translate the cloud-side policy to the device-side policy, they will lose a lot of essential information. Not just a user identity, but also user role, the permission, the life cycle. They are lost in the on-device policy. So let's look at another example of this QuickSet app. So although only authorized user can go through this process and to get a credential assigned by the cloud, and the lock is assured that only authorized user can establish this binding relation. However, the on-device policy still does not maintain the user role, the permissions. It does not differentiate different users who have different permission roles. Based on this vendor design, it only shows different GUI in the app for users of different permissions. A high privileged user will see more control options in the app. A low privileged user, a guest user, will see less control options in the app. But the device really doesn't differentiate the different user permissions. And in a real attack that we performed, the low privileged user can actually send a command, any command to the device. The device will just accept it. That allowed, essentially, basically that means a low privileged user can send a high privileged command to the device. So by further generalization, we find that the device-side policy is not merely a simplified version of the cloud-side policy. So to keep up with the social norm for privacy and security, the device actually needs to maintain certain policies that are not intended to be shared with the cloud. For example, many user-specific attributes, passcode on the device can be privacy or security sensitive that may not want to be shared with the cloud. For example, a authorized user may want to add some offline keypad code on the log. The keypad code allow you to just use the keypad to unlock the door. Usually, the authorized user can use the mobile app to add a keypad code to the door, to the log. Although such a keypad code is security critical, the code is not designed. Based on many vendors, the code is not designed to be shared with the cloud. So generally, by design, the cloud, the QuickSet cloud, for example, does not maintain any credential that can directly unlock the door. So that prevents the single point of failure from the cloud perspective. Consider that even if the cloud is compromised, even if the cloud leaked credential, the attacker cannot directly use any credential from the cloud to unlock the door. So this prevents the single point of failure, that the cloud never stole the actual keypad code. So in spite of this security design, in spite of this security benefit from this design, serious security problems still arise. So we note that there in the IoT, in the IoT usage, there's a user expectation that a device owner may rely on the mobile app, may rely on the cloud side to fully manage the device, to fully monitor the status of the device. Whether there are authorized user on it, whether it's logged, unlocked, whether there are anything, a owner will expect to use the cloud to monitor every status of the device. However, the QuickSet cloud or its app does not show there the access code added by a guest user, authorized guest user on the device. And even after the owner revokes the user, from the cloud side, the keypad code is still there. And the guest user can, even though without permission, can still use that keypad code to unlock the door. You consider in the real world scenario that the malicious guest user can be Airbnb guest, hotel guest, it can be prior employee whose permission is revoked, etc. So we find that for the owner to really clean up this user, to really clean up anything of the prior user, the owner has to go physically near the log. And so her mobile app can, on a specific GUI of the app, the owner can query the log and list all the keypad code stored on the log, and the owner can choose which one he wants to delete. Yeah, of course, this is not made super clear by the vendor, and even with this design, there are still security problems. So first, in the modern usage of IoT, so like the device manager, house owner, Airbnb host, hotel, or generally hospitality services, they often remotely manage devices. They don't really have the luxury to go near the device. They usually remotely manage add guest, revoke guest. They may not always have the luxury to go physically near the log to do all those operations. on the other hand, from the owner's perspective, the full secure manage of IoT is now split into two parts. The manage of the cloud-side policy, okay, the manage of the local on-device policy, and for failing to manage both parts, then you will leave the device into an undesired, unintended status that you do not know. So that really seriously violates the security expectation in the current internet usage of IoT. So the problem that I just mentioned fall into the first category of problem, flaw in the accept model translation. We also have another category of the problem. We may not have enough time to talk about all of them today. I'll just briefly talk about the second category. So as we just, based on what we just talked about, the essential challenge in the MaaG IoT access control is the lack of proper consistency model for the access policy between the cloud and the device. Let's look at another perspective of this. So because the device needs to get, the device needs to think and get policy from the cloud. So essentially, MaaG IoT is inherently network partitioned. And the device are often not connected to the cloud to fetch the latest policy. For example, if there's a revocation on the cloud, revocation of a permission on the cloud, the device may not always get the latest policy update. So as a mitigation, people might think that, okay, the prior eventual consistency model in the distributed system might work here. For example, if we expect some delay, the device will eventually get the policy update when the phone is nearby, or we may even require that as any user, if you want to operate the lock, you have to help the device at least every while to get the latest policy from the cloud to make sure the device, with some delay, but eventually get the latest policy from the cloud. That might be the ideal scenario, but in our study we found that no, that doesn't work. That the prior eventual consistency model doesn't work for the MaaG IoT access control in terms of the synchronization between the cloud side policy and device side policy. This is because the policy sync messages, the policy updates have more complicated causal relations than the prior policy than the prior data synchronization in distributed system. This leaves a tremendous space for attack. Let's look at one example here today. So here is this is another lock, another real-world popular lock called the branded level. So we have the cloud here, the mobile app, the lock. And when the cloud wants to synchronize the policy to the lock, of course, all the messages are the policy sync messages. For example, the M1 message gives the user U1 a permission P1. M2 message gives the same user U1 a permission P2. M3 message gives the same user U1 revoke all the U1 permission. This is and then there are M4 and M5 policy sync messages. M4 gives another user U2 a P3 permission. This gives the user U2 revocation for all her permission. So in the real world, the policy sync messages to arrive at the device may be disordered. For example, this can be the expected order, M1, M2, M3. This is the expected order. But in the real world, the actual possible order to arrive at the device may be M1, M3, M2 because of network partition. So if M2 is received after M3, M2 is to grant a permission, M3 is to revoke all the permission. M2 arrived. If M2 is, arrived late, eventually the device may still give this user a P2 permission, even though we expect the permission to be all revoked. To handle the non-deterministic order, the traditional distributed system often leverages temporal order relation between messages to ensure that an earlier message, if received late, should not overwrite the newer data. However, in the MaaG IoT, the policy synchronization messages have greater logical complexity. For example, both M1 and M2, their order, both M1 and M2 are important to keep, regardless of their order to arrive. They are logically independent. But M1 and M2, relative to M3's order, is important. M3 is to revoke them. Also, the first group of message released to one user. The second group of message released to another user. So the relative order between the two groups are not important. So there's a more complicated logical or causal relation between those messages. And the real world vendors, we found that did not really appreciate the complexity, and their design is usually trivial and problematic. And this leaves a lot of tremendous space for attacks. Consider just one simple attack. The attacker can just, the malicious guest can just manipulate the order of these messages to gain permission even after even though his permission should have been revoked, but he can still reorder the permission granting message to still have the permission after the revocation. And the log cannot simply deny those disordered messages, because in the benign scenario, the message may arrive with the disorder. So yeah. All right, there are more complicated. There can be even more attacks related to the logical relation between the messages, and we may not have enough time to talk about all of them today. And so in general, we find that the problem are general, and we find in all the devices that we purchased and tested, they're all vulnerable to the problems. And or we reported all the problems to the vendor, and most of them have replied and acknowledged. And at least 4 of them have mitigated or patched the problem. All right, so at a few key takeaways. So there are serious design level challenges in the MaaG IoT architecture. Considering the asymmetric access control model between the cloud and the device, they have different access control model, but they want to ensure they are semantically consistent, and to coordinate that's very difficult. And there are two major design level problems concerning the access model translation and the policy synchronization. All right, I think that's all, and I'm happy to take any questions. At least 4. My students checked a while ago. We didn't keep checking. Yeah, but most of them have acknowledged and said that they were patching. Yeah. All right. All right. Yeah, you can still ask me. Yeah, I'm around, and you can still ask me questions or discuss. Yeah, offline. Right? Thank you.